Welcome to the fourth lecture for Chemistry 418. This lecture is on alpha decay. The readings for alpha decay are covered in Chapter 3 of Nuclear and Radiochemistry and Chapter 7 of Modern Nuclear Chemistry. This lecture is going to cover energetics of alpha decay, in other words, the energy related to the decays. We're going to get information from the theory of alpha decay as it's developed between energetics and half-lives. We're going to introduce a term called hindrance factors. We're also going to talk about heavy particle radioactivity. In other words,
the emission of a charged particle larger than the helium nucleus.
We'll introduce the concept that some isotopes have a very, very small branching of a decay of something like carbon-12. And then we'll talk about proton decay. There's a range on the chart of the nuclides, the proton drip line, and we'll discuss the emission of protons from isotopes. As we presented in our very first lecture on the history of modern nuclear physics, Ernest Rutherford and his team identified a positively charged particle being emitted from the nucleus. The helium-4 nucleus was based on observed emission bands. From this point, it was clear that a particle of 2 protons, 2 neutrons was coming out of the nucleus. Now, the energetics of alpha decay, their energies range from 2 to 9 MeV. Originally, they were thought to be monoenergetic. However, fine structure was discovered where the alpha decay energies can vary
for a given isotope.
And as we'll see, what this means is that alpha decay, when it goes to a daughter state, can decay to different levels in the daughter nucleus. Those energy levels differences are based on the differences on the alpha decay. So you can get information on the energy level differences, and those will often be accompanied by gamma emissions. So, for instance, if an alpha decays to a energetic daughter state, that'll be accompanied by a gamma emission that will also be a measurement of that energetic state. And our general trend that we have for alpha decay, as we discussed earlier, is that a parent decays to a daughter. It loses 2 protons. The A changes by 4 because 2 neutrons are also emitted. They're emitted as this alpha particle, and we have this Q value. An example of an isotope that undergoes alpha decay is shown here, Seaborgium-263. It decays, it loses 2 protons, 2 neutrons, so it goes to rutherfordium. The A reduces by 4, so it goes from 263 to 259. And there's a helium nucleus that's also emitted as the alpha particle. The energy, this Q value, we're going to find is really the sum of the alpha energy and the recoiling nucleus energy.
And as we have already discussed, the Q value can be found through calculations or databases. And here's an example of that fine structure as we discussed with alpha decay. Here's an example of an alpha decay spectrum for the decay of thorium-228. We see that there's a few different alpha decay energies observed, and I want to point out that this is log counts versus channel number. The channel number is directly correlated with energy. So we see that there is one peak that dominates, but a few peaks that can be observed at relatively low intensities. This relates to the decay scheme where bulk of the thorium-228 decays to the ground state of the radium-224. There are certain transitions that decay to higher level states of the progeny.
There'll be less alpha energy, and they're accompanied by gamma decay.
And the sum of the gamma and the alpha is equal to the energy from the alpha decay.
So the alpha decay energies can vary for the same isotope, and we know that when we look at the chart of the nuclides, we have different alpha decay energies listed for a given isotope. There are over 350 alpha-emitting nuclei, and as I showed here, these alpha decay energies can be used to develop decay schemes. Fundamentally, all nuclei that are greater than 150 mass are thermodynamically unstable against alpha emission. That means they have a positive Q value. However, the probability of some of those decays are rather small compared to competition from beta, so you generally see alpha with
isotopes that are greater than a mass of 210.
This isn't completely true. As we see here, their energy ranges from about 2 MeV to almost 12 MeV, where neodymium-144 is a very low energy alpha emitter in the lanthanides. Polonium-212 metastable is a very high energy. We're also going to see a correlation between half-life and decay energy, where the neodymium half-life is
almost 10 to the 30th times longer than the polonium-212. And what we're going to find out is that, generally speaking, the shorter the half-life, the higher the alpha decay energy. There are some trends that can be observed with the Q value energetics for alpha decay. One is that the Q value generally increases with A. So if we look at all the isotopes together and we increase A, we see that there's a general trend that as A goes up, the Q value increases. However, this is not generally true for a given isotope. If I look at a given isotope, for instance the lead here or the bismuth here, plutonium here, as I increase the A for a given isotope, the Q value generally decreases. There's also some shell effects that we see with this Q value. We see peaks at N of 126. We also see that there's alpha decay near the 82 neutron closed shell, which is found in the lanthanides. We get an increase in the Q value there since we get an increase in the alpha decay energy. The alpha half-life decreases so that we can start to see some competition between alpha decay and other modes of decay. There's also some short-lived alpha emitters near doubly magic tin 100, and you can examine this on the chart of the nuclides. Look at some of the isotopes that are listed here. And alpha emitters have also been identified by the proton drip line above A of 100. And the proton drip line is that part of the chart of the nuclides, which is right at the very edge, the left-hand edge, so the very, very light isotopes. And A above 100, if you inspect that area of the chart of the nuclides, you'll see some alpha emitters.
As was discussed on the previous slide, there are some regimes where there are light alpha emitting isotopes. Let's explore those areas. One area that was mentioned was near N equals 82, so 82 neutrons. We can highlight those alpha emitting isotopes as shown here. And as you see, fundamentally, these decays drive towards that closed shell at 82. We also showed that there were alpha emitters near tin 100. That would be doubly magic tin with 50 neutrons and 50 protons. And again, the alpha decays in this regime, as shown here, have trends where the alpha decay trends towards the formation of this doubly magic tin 100.
The alpha decay energetics allows us to calculate the Q value and the alpha decay energy for a given isotope. We know that the Q value exceeds the alpha decay energy, and this is due to the fact that the Q value is the total energy of the system, so it's the kinetic energy of both the alpha particle and the progeny. We have a relationship where the momenta are going to be equal in opposite directions for the kinetic energy of the progeny and the alpha particle, so we can use this equation where mass times kinetic energy for the alpha is equal to mass times kinetic energy of the progeny. We can rearrange this equation and we can solve for the kinetic energy of the progeny as a function of the mass of the alpha, the kinetic energy of the alpha, and the mass of the progeny. We can substitute this into the Q value equation, and we get a relationship in which we have terms of the kinetic energy of the alpha, the mass of the alpha, and the mass of the progeny. We can rearrange this is shown here, and we end up with a final relationship where we can say that the kinetic energy of the alpha particle is equal to the Q value times mass of the progeny divided by the sum of the mass of the alpha particle and the progeny mass. From this equation, we see that the bulk of the kinetic energy value is taken up by the alpha particle. So the Q value is often close to the alpha decay energy. From the semi-empirical mass equation, from alpha decay, we know that emission of an alpha particle lowers the Coulomb energy of a nucleus. This increases the stability of heavy nuclei while not affecting the overall binding energy per nucleon.
From the binding energy curve, that the alpha particle is tightly bound and has a very high energy per nucleon in terms of binding energy, and it's similar to the nuclei in the region of alpha decay. So this is the energetic reason for alpha decay rather than proton decay. And it's this tight binding energy from the alpha nucleus, which is greater than a single proton. So this is the fundamental explanation for alpha decay. The alpha emission lowers the Coulomb energy in the nucleus. The alpha particle has a high binding energy per nucleon, similar to the nuclei that are emitting the alpha particle. Therefore, the parent and the progeny have approximately the same binding energy per nucleon. So this means that the alpha particle can be emitted and increase the stability of the nucleus in terms of Coulomb energy, but not have a great change in terms of binding energy per nucleon.
We can use the calculations that we discussed to evaluate Q values for reactions. So as an example here, if we wanted to evaluate the Q value of the decay of uranium-238 to thorium-234 plus an alpha, if we get the mass excesses of uranium-238, thorium-234, and an alpha particle, we arrange this equation. We can see that the Q value is 4.27 MeV. Then we can use this to plug into our equation here and calculate from the Q value what is the alpha decay energy. We see that the Q value is 4.27 and our alpha decay energy is 4.198 MeV.
Again, as we discussed in the previous slide, Q value energy is divided between the alpha particle and the recoiling progeny. The kinetic energy of the alpha particle will be slightly less than the Q value, and this Q value that's calculated may include the gamma decay energy. So if one were to look at data, one would see that the sum of the alpha particle energy and the gamma energy would equal the kinetic energy calculated from the Q value. If no gamma decay is present, then the alpha particle has all the calculated energy. And again, this comes from the conservation of momentum and those equations that we discussed previously.
One interesting observation about these energetics is that the alpha particle energy is far less than the Coulomb barrier
Of the alpha particle and the progeny.
So in other words, the energy that it takes for an alpha particle to leave the nucleus is much, much less than the energy needed to push that
Alpha particle into the progeny to reform the nucleus.
And we can evaluate this by evaluating the Coulomb barrier. And here's our equation that we'll use for the Coulomb barrier.
The generalized Coulomb barrier equation includes charges, radii, and a collection of constants. The charges of the approaching nuclei are multiplied together and divided by the sum of the radii, and these are multiplied by the charge, 4 pi, and the electric constant. Applying this specifically to alpha decay, we get 2 for the z of the alpha particle, the z of the progeny. We use the equation for determining nuclear radii, where we use r sub naught as 1.2, a of the progeny to 1/3, plus the a of the alpha particle to 1/3, and this is all multiplied by 1.44 MeV Fermi, which is a collection of the constants, where a Fermi is 1 femtometer.
So let's look at this for uranium-238. The alpha particle Z is 2.
The progeny
Would be thorium, so we use a Z of 90. We put in the values 1.2 times A
progeny to the 1/3
plus helium nucleus to the 1/3 times 1.44 MeV Fermi. And what we get is a Coulomb barrier of 28 MeV. So this says the alpha decay energy, while it emits with on the order of 4 MeV, to reverse the reaction would take 28 MeV. So the alpha decay energies are small compared to the energy required for the reverse reaction.
This observation that the alpha decay energy is much less than the Coulomb barrier, in other words, the energy of the alpha particle that's emitted from the nucleus is much less than the energy required to push the alpha particle into the nucleus, will be used in the modeling of alpha decay.
As we discussed earlier, alpha particle emission can often demonstrate fine structure. And this is due to the fact that during the decay, the
Parent can decay to an excited state of the progeny.
and this is often due to the fact that the
Progeny nucleus
and the parent nucleus spin and parity need to match up to a certain degree. So for instance, californium-249, it goes to the 9th excited state of curium-245 because that is the lowest lying state with the same.
parent spin and parity. We will discuss this in more detail.
so that we can understand why certain isotopes have fine structure and certain don't. For instance, even nuclei, since their spin and parity is 0 plus, will often decay to the ground state of the progeny because their spin and parity is 0 plus, and the alpha particle also has 0 plus spin and parity. We can also observe long-range alpha decay, which is really the decay from a metastable state to the ground state of the progeny. For instance, polonium-212M sits about 3 MeV above the polonium-212 ground state, and it decays to lead-208 directly with an alpha particle of about 11.5 MeV. And what's interesting about lead-208 is magic nuclear properties of lead-208 can help drive that decay from the metastable state all the way to the ground state of the daughter. There are some systematics that can be observed from alpha decays. We've already discussed the Coulomb potential as a way of accelerating the higher mass products out of the nucleus. And with a larger mass, it's often observed, so larger A's that decay, the progeny and alpha particle can start further apart within the nucleus. So that's another reason that this potential exists, so that alpha decay occurs with higher A nuclei. One of the things that we can observe through alpha decay is some effects of the mass parabola from semi-empirical mass equations. This example is shown where alpha decay occurring and with accompanied beta decay. So as we see, as an example here, we get a decay from a higher state through alpha, and we observe beta decay because once the isotope is on this mass parabola, it can go to the lowest state. The other thing we observe is we get areas where we can get branch decays. So where there's probability of either a decay through beta or a decay through alpha. So this is why we can get branched decays within the decay chains for uranium and thorium. Using what we've discussed, we can start thinking about how alpha decay occurs in the nucleus and develop alpha decay theory.
We'll show this using uranium-238 as an example.
The distance that the closest approach for a 4.2 MeV alpha particle can make to a thorium nucleus, so similar to this uranium-238 decay that we were discussing, is about 62 femtometers. So if we look here on this potential for a nucleus, the 4.2 MeV, the alpha particle, would get about this far and then be repulsed by the Coulomb barrier. So the alpha particle shouldn't get anywhere near the nucleus. So if we look at the nuclear potential, the alpha particle would be sitting right about here on the order of 4 MeV above the ground state. And if I look at this from a classical component, the alpha particle should be completely trapped behind the nucleus. There's a barrier up here. Now, wave functions are only completely confined by infinitely high energy barrier, so the energy potential, we can go all the way up. We have a Coulomb potential, so it's a finite size. There is the main component of a wave function that describes where the alpha particle can exist would be inside the barrier, but there's also a finite component that's going to be outside the barrier. So there's a probability of finding the alpha particle outside the barrier. And this is what we call in quantum mechanics tunneling. So the trapped particle has a component of the wave function outside the barrier potential. So there's a probability, however small, of it appearing outside this barrier. And there's a probability that it would go through this barrier. In fact, we can show that this probability of penetrating the barrier has to be related to the decay probability. So we should be able to determine something about the decay constant related to this barrier. Now, higher energies are going to have a higher probability of tunneling through this barrier. And as an example, imagine that we have two different energies shown here, one here, one here. The amount or the distance that these different energies would have to penetrate through the barrier is different. The higher energy has a shorter barrier potential, therefore it would have a higher probability of tunneling through that barrier. And this is why we see a relationship between a shorter half-life and a higher energy. Imagine if you were very close to the Coulomb barrier, you have a very small barrier to penetrate through, so the probability of penetrating the barrier would be very high. And that's the other thing that we see, is that we can determine when we talk about the Coulomb barrier. This is what it looks like when we describe the nuclear potential. So one of the manifestations of this model we just discussed is that the closer the particle energy is to the barrier, the more likely the particle will penetrate that barrier. Also, a more energetic alpha particle will encounter the barrier more often. If we think about the kinetic energy, the mass would be the same, velocity would be greater for a more energetic particle. Fundamentally, the probability of penetrating a barrier is a consistent factor. The more times I hit the barrier, the more times I can sample that barrier, and the higher the probability in a given unit of time will be the manifestation of penetrating that barrier. Since the particle is going faster, it'll hit the barrier more often in a given amount of time. So this goes also to drive the increase of probability of barrier penetration. Now, one theory called the Geiger Nuttall Law of alpha decay, and here's two examples of it. It's fundamentally the same figures, just plotted a little bit differently. And we see that there's definitely a relationship, and this is a log-log type relationship, where we see that the log of the half-life is equal to two constants, a plus b divided by the square root of the q value. Now, the constant for any a and b are going to be dependent upon the z dependence. And one thing I want to show here is the figures. As we see, we have different z's, so different elements. And we also have the same thing here, but I want to point out that uranium-235 does not sit on this uranium line. These are all even isotopes. So if I take an equation that I derive for an even isotope, and I try to use it for an odd A isotope will not fit on that equation. Now, the simple relationship can describe data for alpha decay for over 20 orders of magnitude in decay constants or half-life. And what's observed is that a 1 MeV change in alpha decay energy can result in a change of about 10 to the fifth for the half-life. So we have this dependence on half-life and Q value that we've discussed earlier. The Geiger Nuttall relationship, as we discussed previously, is a very simple and straightforward model to describe alpha decay and half-life. Now, there's models that are available that can be more accurate and take into account closed shell information. An example is given here, the Hatsukawa Model. And this can be, obviously there's empirical fits here, there's corrections for how close or how far one away is from shell parameters, so this is Z dependence. But one thing about this model that's shown is that there's relationships between the progeny A, the Q value of the alpha, and the progeny Z. So they're pretty straightforward relationships that are also reflected in the Geiger Nuttall Law.
A more accurate model, such as the Hatsukawa model, is just provided as an example. For the course, we'll focus on the Geiger Nuttall equation.
One theoretical description that can be used to try to universalize how alpha decay occurs is trying to break up the alpha decay into two factors. One factor is a rate in which an alpha particle appears inside the nucleus. In other words, in order for the alpha particle to escape the nucleus, it has to be there in the first place. We can call that factor this frequency factor. How often does that alpha particle appear in the nucleus? And then there's the second factor, which is, okay, once that alpha particle appears, what's the probability of it getting through the nucleus? So some sort of transmission factor, right? So this factor's here, we can call that P, the transmission factor. Taken together, we can take the transmission factor and the frequency factor to get something about the decay constant for alpha decay. Now we have an additional factor, this preformation factor of the alpha particle in the nucleus, that can help us describe alpha decay theory in more detail. Unfortunately, we really have no clear way to calculate from first principles this preformation probability. We can use empirical data, and fundamentally the difference between the theoretical estimates and the observed emission rates can be used to evaluate what the preformation factor should be. So basically, we can use the preformation factor as a fit for our data. Now, we can use the velocity of the alpha particle as a way to determine how many times the alpha particle will impinge upon the barrier. And we know that we can use that as frequency of how often the alpha particle will impinge upon the barrier, basically related to the velocity of the alpha particle. And if we can calculate the radius of the nucleus, we've already discussed how to do that, we take twice the radius. That's a distance that the alpha particle would need to traverse, and that's on the order of femtometers. We can get information about the alpha velocity from the kinetic energy, and we can use 1/2 mv squared. In all actuality, that's a lower limit for the velocity because a particle, since it's moving in a potential well, the velocity could be greater. And what we find out is that the alpha particle can impinge a nuclear barrier on the order of 10 to the 21st times a second. So we can utilize this equation, which is shown here, that some frequency is equal to the velocity divided by twice the radius. We can relate this to the Q value, the Coulomb barrier, and this term mu, which winds up being the reduced mass. And this is just a function of the mass of the alpha particle and the progeny. There's an equation, the Gamow equation, which is listed here, and this can be used to evaluate the decay constant for alpha decay. We can determine that decay constant from the potential. Here's our nuclear potential, and fundamentally we've got some energy here, T. The alpha particles at this energy, so what's the probability of it penetrating this barrier? That's all we're really interested in. And we get this equation that's listed here. And with the terms of this equation, it's a constant, 2, the mu, that's our reduced mass factor. We have R's, R1, R2. Well, those are just the distances that it needs to penetrate the barrier. So the R1 is here, R2 is here. So we integrate from those terms, and these values here, those are just our potential terms for the nucleus, where here's 1 energy potential, and T is the kinetic energy. We can use this equation, use the square well potential, integrate and substitute. The equation comes out to be this term, where we get the decay constant is equal to a number of factors. The Z terms here, the large Z is for the progeny, and the lowercase z is for the alpha particle, where z is the proton number. And we also have some other terms here, t and b, which are just functions of z, the radius, or we can talk about it in terms of the mass, and the b and the radius. So this calculation we just described, with all the terms, can actually be rearranged to evaluate the half-life. We know the half-life is log 2 divided by the decay constant, so we substitute those terms in. The decay constant is just this frequency factor of the probability. We discussed the Gamow term, which is shown here, so it's log 2 divided by this factor, e to the minus 2g. G is a Gamow factor. And what this rearranges to is something very familiar. It just shows the Geiger Nuttall relationship that Gamow also predicted. These factors here are specific for a given nucleus, and if we derive the terms in log of the half-life is equal to 2 constants, these constants can be used to evaluate terms of the nucleus that are related to the Coulomb barrier and the Q value. Now, one thing about these equations is that the calculated emission rates are typically larger than the observed rates, and what this means is that the observed half-lives are longer than predicted. This difference can be used to evaluate a preformation factor. So if we think about it, this model can describe the alpha particle emission if the alpha particle always exists in the nucleus. The fact that the half-lives that are observed are longer than predicted gives us a factor that can say, well, what's the actual probability of having this preformed alpha particle in the nucleus? So the preformed alpha is a way of fixing the data so that our calculations and observed data can match. And we just use the preformation factor as a fix. And we can evaluate the difference between calculated and measured half-life, and this figure is shown here for even nuclei. So these tend to be ground state to ground state. The average preformation factor is about 10 to the minus 2. This means about 1% of the time the alpha particle is preformed in the nucleus. So if we say here, this is the ratio of the calculated to measured half-life, and we can say, well, we can fix this data so it works by having a preformation factor of 10 to the minus 2. Now, everything we discussed related to the model really holds for even nuclei. If we have odd, even odd, or odd, even nuclei, the half-lives are even longer than predicted due to something we're going to call hindrance factors. Now, the model assumes the existence of preformed alpha particles in the nucleus. And the ground state transitions from nuclei containing odd nucleon can only take part if that odd nucleon becomes part of this emitted alpha particle. So if I think about it, if I have an odd nucleon, that means that the highest energy nucleon in that nucleus is unpaired. In order for that to become part of the alpha particle that's emitted, a nucleon pair has to be broken. So this is a pretty unfavorable situation because the alpha particles can already be formed from existing even pairs. So this gives rise to this observed hindrance. And the alpha particle needs to be composed of existing pairs in such a nucleus. The product nuclei is going to be in a higher state. This can also explain why there's a high probability of transitions to excited states in the daughter nuclei. Now, the hindrance factors have been evaluated, and they're generally between 1 and 3 times 10 to the 4th. There's 2 ways of evaluating the hindrance factors. They're listed here. One, we can make a ratio of the measured alpha decay half-life or the calculated alpha decay half-life. Or the converse of that is I can do a ratio of calculated alpha decay constants over measured alpha decay constants. Either way, I'll get the same hindrance factor. This is because, well, there's a relationship between the decay constant and the half-life, where log 2 divided by the half-life is equal to the decay constant. But this is an important equation to remember, and use this to determine the hindrance factors. And it doesn't matter if I take the ratio of the alpha decays or the ratio of the decay constants. What you should remember is that the values are going to be greater than 1. So if you use an equation and you make a calculation and the hindrance factor is below 1, chances are all you need to do is take the inverse of that. Now, why we can calculate these hindrance factors, they're actually available in the table of the isotopes. As an example, let's look at the transition of americium-241 to the neptunium-237 via alpha decay. Here's the data in the chart of the nuclides. We get the half-life of the americium-241, its spin imparity, the Q value, and then a bunch of these numbers that are listed here. And these are our hindrance factors. So states of neptunium-237 that are in the 5/2 plus ground state and 7/2 plus the first excited state have hindrance factors of about 500, and you can see those values listed right over here. So we can say that this isn't a particularly favored transition. However, the americium-241 sits in a 5/2 minus state right there, and if we see that there's a 5/2 minus state right here, the main transitions go from that 5/2 minus state in the parent to the 5/2 minus state in the daughter. And these are practically unhindered transitions. We see the hindrance factor is just barely over 1. And the reason for that has to do with the similarities between the spin and parity states of the parent and the daughter. The spin's the same, the parity is the same, so there's no hindrance. We see that the ground state, the spin is the same, but there has to be a parity flip, so that's going to increase the hindrance. As we can see, the values can go anywhere from 1 for a hindrance factor to thousands. And as we see again, this relationship is driven, this spin and parity state from the parent to the daughter being the same is manifest by a low hindrance factor. So we should be able to evaluate something about changes in spin and parity as it relates to is that there's 5 classes of hindrance factor that are based upon some values. We can describe the transitions as favored or less favored. If you have a hindrance factor between 1 and 4, the transition is a favored transition. So the emitted alpha particle is from two low-lying pairs of nucleons. Hindrance factors between 4 and 10 indicate a mixing or favorable overlap between initial and final nuclear states. 10 and 100 usually means that the spins of the initial and final states are going to be the same, but the wave function overlap is not favorable. Higher factors indicate that a change in parity is going to occur, but with projections of the initial and final state being parallel, and hindrance factors of 1,000 or greater indicate that the transition involves a parity change and a spin flip. So the more fundamentally from this information, hindrance factors go up when changes from the parent to the daughter become more involved in terms of having to change spin or having to change parity. There is probability of emitting other particles than alpha particles from the nucleus. These are generally much less probability, however they can be observed. An example is carbon emission. Now one would think that carbon-12 would be emitted from the nuclei. You can think of it as a multiple or three alpha particles together. And if you were to look at the radium isotopes, they could decay towards doubly magic lead-208 through a carbon-12 emission. Now, by inspection of the table of the isotopes, you can look at radium 222 and radium 223, and you'll see that there's a small branch of carbon-14 emission. This, the reason that there's a bit of a neutron excess is this favors emission from neutron-rich light products. Now this emission probability, if you look at the table of the isotope data, is extremely small compared to alpha emission. This barrier model that we discussed, however, can be applied, except the only difference between alpha particles and carbon nuclei would be their mass. And also, if you think about the probability of the preformation of a carbon-14 residual inside of a heavy nucleus is also small. So that's why we get very small probabilities.
The simplest example of a positive charged particle decay is the proton decay. We've explored the alpha particle, which is the most common. We discussed larger charged particles, such as carbon isotopes. And now let's just focus in a little bit on the simplest charged particle, which would be a proton decay. So for proton-rich nuclei, they have a Q value that can be positive for proton emission. And if we look at the chart of the nuclides, here the expanded version of the mass number versus the atomic number, we know that there's boundaries, and at this boundary you'd find the proton drip line. So these are going to be proton-rich nuclei. On the other side, you'll find a neutron drip line, same sort of property where the neutron just kind of falls off. And these are obviously neutron-rich nuclei. So we've got this proton drip line where the Q value is positive. And this can also be used to explore and enhance understanding of how a proton stays within the nucleus. The decay theory of proton decay can be similar to alpha decay. However, there's no preformation factor for a proton, right? For the alpha particle, we need to have two protons, two neutrons get together. For the proton, well, the proton's just sitting there. The other difference is that proton decay energies, even for heavy nuclei, are relatively low, 1 to 2 MeV. So this means that the barriers are pretty large and the probability of penetrating those barriers generally low. We need to go to some pretty exotic areas of the chart of the nuclides to explore these decays. And here's an example of some low Z elements with their isotopes that decay by proton emission. If we look at fluorine 15, 16, oxygen, right? Oxygen 12 has 2 proton decay. 13, there's a probability of this proton decay. Nitrogen 10, there's proton decay. Nitrogen 11, proton decay. Carbon 8 has a proton decay. And then there's a probability for carbon 9. So these are all very proton-rich, nitrogen-deficient isotopes that can undergo this decay. And you can find where they're located by exploring your chart of the nuclides and looking for that proton decay symbol, either 2-proton or a single proton decay. In this lecture, we reviewed alpha decay and we explored the systematics between energetics and alpha decay. The key of trying to understand alpha decay and some properties of the nucleus is really correlating energy decay with observations. Some of the things that were observed that we discussed was the correlation between half-life and Q value. Those decays that have a higher Q value, higher energy, tend to have a shorter half-life. We demonstrated how we could calculate Q value for alpha decay. There was also an understanding that the Q value is the entire energy of the system, and the alpha decay, the energy of the alpha particle, takes away most of the energy, but there is also some recoil that goes to the daughter. And one thing that should be pointed out, this recoil energy to the daughter can be on the order of kiloelectron volts, keV, and if you remember that bond energies are generally measured in the order of EV, this can be enough energy for the daughter to break bonds, and this actually occurs. There was also discussion on fine structure and alpha decay. In other words, alphas often just don't produce one alpha energy. There are different alpha energies, and that has to do with the decay of the parent to the daughter ground state and excited states in the daughter. Those are often accompanied by gamma decays. We'll discuss this more when we discuss gamma decay in the course. Now, we went over a few models for alpha decay, and what's important so much the models utilization, but understanding the trends in the models and how they were derived. Some of the trends that are observed is that alpha particles at higher energy impinge upon the barrier more frequently. This is due to the fact they have a higher energy. If you use 1/2 mv squared, their velocity must be greater if they're at higher energy. Also, if they're at a higher energy, the barrier that they have to penetrate is smaller, so there's a higher probability of that particle penetrating the barrier. And we also talked about the preformation factor, that an alpha particle may not always be sitting in the nucleus, that it needs to be formed in the nucleus and then impinge upon the barrier. So this can account for some of the delays that one sees between the model and the observations, particularly for non-even nuclei. We talked about tunneling and potentials. So it's an application of the tunneling phenomena where the particle, the alpha particle in this case, needs to overcome a barrier, and it overcomes that barrier not by going over it, but by tunneling through it. Of course, this accounts for very long half-lives, and this also accounts for the large range of half-lives that can be observed for alpha decay. We described some of this hindrance of alpha decay, which is basically the ratio between the model and the observation. The larger that ratio, the more hindered that decay is, and we can describe that hindrance through a number of phenomena, including changes of spin and parity. And we'll see this is even more manifest for beta decay. We also touched upon other charged particle decay, including proton emission and carbon emission, including carbon-12 and carbon-14.
Examples of questions you should be able to answer based upon the lecture are provided here. One has to do with alpha decay energies from decay. An example with thorium-228. Why does thorium-228 exhibit multiple alpha decay energies? This was discussed in the lecture. This is another thorium-228 decay scheme that's shown. Here's the parent, thorium-228, decaying to the radium-224. And we see that it decays to multiple levels in the radium-224. 28.2% of the time it goes to this first excited state, and then 71.1% of the time it travels to the ground state. The alpha decay energy for this ground state is different by 84.3 keV from this first excited state, and they'll show up as different peaks for the alpha decay energy. So that's why we get this difference in the alpha decay energies, because the alpha decay goes to different states in the nucleus. For an even nucleus, like thorium-228, that primarily decays to the even ground state of the progeny. What are some alpha decay energy ranges that can be observed? Well, the lowest energy that's observable is neodymium-144 with an alpha decay energy of 1.8 MeV, and then polonium-212M for the metastable state decays with an energy of 11.6 MeV. So that's a reasonable range for alpha decay energies. Generally, they're between 4 and 6 MeV.
What is the relationship between the Q value and the alpha decay energy? Well, the alpha decay energy is equal to the Q value times the mass of the progeny divided by the sum of the mass of the alpha particle and the mass of the progeny. The Q value is therefore the recoil energy of the progeny and the emission energy of the alpha particle.
So you can use this equation to use the Q value to determine an alpha decay energy. So imagine that we want to determine the alpha decay energy for an isotope like plutonium-244. It has a Q value of 4.665 MeV. Find the alpha decay. Well, plug this value into the equation. There's our Q value.
Plutonium-244, the progeny is uranium-240.
So 240 divided by 240 plus 4, that's equal to 4.589 MeV. And if you looked in the chart of the nuclides, you would see that that is one of the alpha decay energies for plutonium-244. You would also see that there are other values that are available. Again, that has to do with decaying to excited states. Even this value, that's the maximum alpha decay energy that can be obtained from a given Q value. Based on the results from the lecture, you should be able to discuss some general trends that are observed in alpha decay, and examples could be that alpha emission is generally seen for the heaviest nuclei in the chart of the nuclides, generally with isotopes of mass greater than 210. So these are the elements above lead and bismuth generally. There are some examples of alpha decaying isotopes in the lanthanides. For instance, we discussed the low energy alpha decay that is seen in neodymium-144. The other trend is that the higher energy alpha decays tend to have shorter half-lives, and that the energy of an alpha particle generally increases with the atomic number of the parents. So as we go higher and higher along the periodic table or in the chart of the nuclides, we'll see that alpha decay energies generally increase. So what is the spin and parity
of the progeny from
uranium-238 alpha decay? Well, we discussed this earlier. We gave an example with the thorium-228. The ground states
spin and parity of parent, progeny, and alpha particles from decay are 0 plus.
You go from an even nucleus to an even nucleus. Even nuclei have a spin and parity of 0 plus. How is quantum tunneling related to alpha decay? A topic that's popular in quantum mechanics. We know that the alpha particle, the energy is less than the Coulomb barrier. Somehow the alpha particle can escape from the nuclear potential with less energy than the potential itself. And this occurs by the alpha particle tunneling through a portion of the barrier. The penetration of the alpha particle, that probability, is greater at higher energy, and that relates to a shorter half-life. So what's the relationship between half-life and alpha decay Q value? Well, there's actually an equation that we talked about where the log of the half-life is equal to constant A plus B divided by the square root of the Q value for the alpha decay. A and B are functions of Z, so a function of proton number, and there's strong correlation for even nuclei. You could determine these factors by plotting the log of the half-life in the same unit, generally seconds, against 1 divided by the square root of the Q value for even nuclei of a given Z. So you can do it for uranium and plutonium, thorium, and achieve these relationships that will give you factors for A and B, and you'd be able to determine the alpha decay half-life for isotopes that are theoretical or have half-lives that are long enough where other routes, such as spontaneous fission or perhaps beta decay, compete. Based upon the lecture, one should be able to answer some questions on the Coulomb barrier, such as what is the generalized equation to find the Coulomb barrier. The generalized equation is shown here, where nucleus 1, nucleus 2, values for the Z are multiplied together and divided by 1.2 times a to the 1/3 for nucleus 1 and nucleus 2, and that's multiplied by 1.44 MeV. We'll see in other examples for Coulomb barrier that this equation can vary, and a lot of it has to do with what nuclei were evaluated to derive the equation. And if we make this specific for alpha decay, for Z1 we can substitute 2, and for A1 we can substitute 4. So for an alpha decay, you would be looking at the Coulomb barrier from the alpha decay with Z2 and A2 representing the proton number and A of the progeny. We could use this equation to compare the Coulomb barrier for the alpha decay of plutonium-228, plutonium-244, that's a long range of the same isotope, and then curium-244, so comparing the same A but different Z. What we get for the Coulomb barrier for plutonium-228 is 28.8 MeV. If we just add neutrons, so we go from 228 to 244, we're fundamentally diluting the charge, so the Coulomb barrier goes down, and as we see, it goes from 28.8 MeV and lose about half an MeV to 28.3 MeV. Now, if we take 244 nucleons, but we convert more of those from neutrons to protons, we're increasing the charge. The Coulomb barrier should go up, and indeed, from this equation, we see that it goes up from 28.3 MeV to 28.9 MeV. Then a final question you should be able to answer based on the lecture includes, what is alpha decay hindrance factor? Alpha decay half-lives tend to be longer than expected based upon models developed for even isotopes. So this hindrance factor is that ratio of either the measured alpha decay half-life divided by the calculated half-life, so this is greater than 1, or the decay constant that's calculated divided by the decay constant that's measured. This is also greater than 1. So you can use either the decay constant or the half-life. Again, make sure the half-life units are the same or the decay constant units are the same. And you should always remember that the hindrance factor is 1 or greater. There's other questions that you should be able to answer that we're not going to give examples on. For example, with other charged particle decay that use similar models to alpha decay, fundamentally proton decay, which occurs with the proton drip line, or other charged particle decay such as carbon-12 or carbon-14.
When you have completed the lecture, please respond to the Lecture 4 quiz and comment on the blog. The information that one should take away from this lecture is listed here. This includes that the alpha particle is the helium nucleus. We've discussed this in previous lectures, just re-emphasizing it here. You should also understand that there is fine structure associated with the alpha decay. An isotope can have a number of different alpha decay energies. This is shown on the chart of the nuclides, for example. Transitions to ground states or excited states in the progeny result in these different energies, and transitions to the progeny excited state also are often associated with gamma decay, and we'll discuss this more in the lecture on gamma decay. You should be able to identify some generalized trends for the Q value for alpha decay. Generally speaking, the Q value increases in energy for A over all alpha emitters when they are compared. However, for a given element, the Q alpha tends to decrease with increasing A. Alpha emission is generally seen in the region where isotopes have an A greater than 210. However, low energy alpha emitters are observed near N equals 82, a closed shell, and near tin 100, which is doubly magic. The Q value for the alpha decay is the total energy for the alpha emission. This total energy is distributed between the alpha particle and the progeny. You should be able to use the Q value to calculate the alpha decay energy, and you should remember that this is for a ground state to ground state transition. The equation that would be used to calculate the alpha decay energy from the Q value is shown here. This lecture also discussed why alpha decay occurs. There are two driving factors. One is that the Coulomb energy of the progeny is reduced compared to the parent because you're releasing 2 protons along with the 2 neutrons in the alpha decay. And the binding energy per nucleon is similar for the parent and the progeny. This is because the alpha particle also has a high binding energy per nucleon. You should be able to calculate and compare the Coulomb barrier to the alpha decay energy. And you should see that the alpha decay energy, or the alpha Q value is small compared to the Coulomb barrier. There are some aspects of alpha decay theory you should take away from this lecture. One is that tunneling is important in alpha decay, and tunneling frequency is a term that we use to describe a property of the nucleus for alpha decay. We also discussed the Geiger Nuttall Law, and the Geiger Nuttall Law is shown here. We went through how the Geiger Nuttall Law can be derived from other nuclear models. And for this course, the Geiger Nuttall Law will be the primary model we'll use for alpha decay. We should also understand the preformation factor. What is the probability of finding an alpha particle ready for emission in the nucleus? And this preformation factor is related to hindrance in alpha decay. You should be able to identify and measure hindrance factors. We also discussed other charged particle emission, including proton decay and heavy particle decay.